Hello everyone. In this video, we're going to talk about some basics of partial differential equations or PDEs. I know most of you in your undergrad, you pass a course on ordinary differential equations or ODEs. But although many of you see PDE equations, differential equations, here and there in different courses, you might not really have a formal introduction to these important equations that happen a lot in engineering and how to solve them, if possible, analytically or numerically. So here are three of these equations that you see in especially mechanical engineering. The first one, that is the second partial derivative of u with respect to t is c squared second derivative, partial derivative of u with respect to x, where u here is the displacement, is what we call the wave equation in a one-dimensional media. So for example, if you have the, so this is the wave equation, as I said, right? Let me write it down for you. Correct. So this is the 1D wave equation. And c here is the speed of propagation of the wave. So for example, if you have a string and you fix it between 2 points, correct, and then give it some initial displacement and let it vibrate, like for example when you are playing guitar or any other type of musical instruments with strings on them, then you're going to see that the string starts showing different modes of vibrations, right? The combination of them, that's a vibrations topic, and that's what you see in vibrations. And so here u, as I said, is the displacement between any point with its equilibrium position. So if you consider this direction x, then here this displacement is u, and the fact is not only this u is a function of x, the position along the string, it is also a function of time, correct? So this u here is a function of both x and t, and the governing equation for this u is what you see here. Again, c here is the speed of propagation of the wave in the string, and you can show that c squared, this guy, or c itself, is the square root of t over mu, where t is the tension, the constant tension in the string, and mu here is what we call the excuse me, the linear density, the linear mass density of the string. So it is m over L, right? If the mass of the spring is m and the length of it is L, then m divided by L if it's uniform. If it's not uniform, dm over dl could be mu of x in general, but here we assume that mu is constant, t is constant. So this is the wave equation, right? And you see this equation in vibration of continuous systems. Now, what's the solution? Well, the solution does depend on these end conditions here that we call the boundary conditions. So if this is, let's say, x of 0, and this is x of L. Now, since this is a partial differential equations, not only you need what we call boundary conditions, so what happens at the two ends of the string, but also you need some initial condition, what happens at time of 0. And since the order of this PDE with respect to t and x is both second order, you need two boundary conditions and you need two initial conditions. So the solution depends on what you have in the beginning of the vibration and at the two boundaries. So you probably have something like, for example, u at, since this is x and t, u at 0 and t, which is the displacement at the beginning point at all times, is equal to 0, let's say. And for example, u at L and t is also 0. So you fix the two ends, and the two ends cannot go up and down. Okay, so these two, as I said, we call the boundary conditions. How many of them do we need? As many as the order of the partial differential equation with respect to position, x here, which is 2. Then you also need two initial conditions. And the initial conditions, they come from the initial position of the whole string. I'm sorry, I just don't know why I'm calling it string over and over, string. And this is like u of x at time 0. What's the initial position that you give to the overall string at time 0? So this is like a function f of t, right? So initially, how would you deform the string? Like when you're playing guitar, how would you pull this string in the beginning, and what kind of function do you give it? Do you give it something like this, or do you lift the whole thing so it is kind of like a half sine function or something, right? And then your initial velocity, which is u with respect to time of x and at time 0, correct? The initial velocity of different points at time 0. So let's say this is a function like g of t. Like if you release them all from rest, then just g of t is 0. If no, you give them some initial displacement, but also you have some initial velocity, then this g of t could be a general function of time. So these two, we call what? We call them, of course, initial conditions. Again, how many of these do we need? As many as the order of your PDE with respect to time. And again, you see it's 2, so I need 2 of that. Okay, so the solution of this wave equation does depend on what you describe for boundary and initial conditions. Okay, and what kind of domain you have, what kind of shape you have for the area over which this wave is propagated. Correct? So this is one example that you'll see in vibrations. Good. Now, another case that you see, for example, is this equation, which is quite similar to the top one, except that order of the derivative with respect to time is first order, the order of the derivatives with respect to position is second order. And if you know, this is what we call the 1D heat conduction equation, right? And this is what you see in your heat transfer course probably in the beginning. So this is the 1D heat conduction. So, for example, if you have a piece of metal or any other material, a bar, and there is some heat coming in here, and there is some heat going out, and this guy here has, this material has a density of rho, specific heat of C, and conductivity of K, correct? So this is Q1 dot, this is Q2 dot. Then the difference between these two heat fluxes, Q1 dot and Q2 dot, is going to change the temperature in this piece of metal, right? If Q1 dot is bigger than Q2 dot, then you have a positive heat influx, and so the temperature is going to go up. If Q2 dot is bigger, then the temperature is going to go down. And the governing equation will be just like that, with the difference that U here is going to be T. Okay, so here at any position, if you start the position along this material, if you started from, let's say, x of 0 to, let's say here, x of L, correct? And at any point x, you measure the temperature T, which is a function of position and it's a function of time. Then your equation, as you can see over there, is going to be partial derivative of T with respect to time is going to be c squared second partial derivative of T with respect to x. Now, the c squared here for this problem, you can show it is going to be k over c times rho. Okay, so we call it the thermal diffusivity, and this depends on the material. Okay, so that's what you have. Then this c and that c are different thing. Okay, that c is just a general constant. This C is the specific heat of this material, right? The bigger it is, the more heat influx you need, the more energy you need to raise the temperature. So this is the wave equation, the 1D heat conduction equation. And again, you see that in heat transfer. Again, the solution of that depends on what you can do to the two ends. Is the heat transfer at the two ends coming from convection, coming from another material through conduction, and so on? And then what was the temperature of the media of the material at time 0? Now here, since the derivative with respect to time is first derivative, you only need one initial condition, but you still need two boundary conditions, okay? So that's the case of this that you see in heat transfer. And then the third one, which we call the Laplace equation. So if this right-hand side is 0, we call it Laplace equation. If it is not 0, we call it the Poisson equation. And this also happens in a bunch of different engineering applications, in electric fields, magnetic fields, in flow of fluid, which are not compressible and not rotary. It is in distribution, 2D distribution of temperature within a plate and so on. So you're going to see this guy a bunch, even in, let's say, computer vision. You see this operator, this Laplacian operator, which is the second derivative of anything with respect to u plus second derivative of this with respect to y. So this is called del squared or nabla squared. This is del squared of u, and this is called Laplacian operator equals 0. So if you see, that's another way to show it. And this is a measure of a smoothness of u, and this is used again in applications like computer vision when they want to calculate stuff like optical flow and so on. One of the ways, one of the constraints they use is they want the image velocity or optical flow to be smooth. Then they put some limitations on this entity. So I'm not going to get into that because my main focus is mechanical engineering here. But later, when I develop my videos for computer vision and image processing, and I talk about optical flow, you're going to see this guy again. So as I said, for example, for temperature, you can show that if you have like a 2D media, a 2D plate or something, and at each position, so let's say if you call this axis x starting from here, and this axis starting from that bottom left corner, so this is the origin, y, then at each point x and y, you can have temperature T, which is a function of x and y, and this is for the steady state case where the T is not a function of time anymore, right? So you put some, let's say, for example, you have some specific boundary conditions, 2 with respect to x, 2 with respect to y. You give it some initial temperature at different points, and let the temperature distribute over this object with respect to the boundary conditions you have, correct? And based on that, the temperature would be distributed based on, as I said, the material property of this object and based on these boundary conditions. So like which side has convention, which side is sealed, right? So for example, you might say these two sides are gonna make sealed, and then these two sides are gonna have convention. Okay. So it means the partial derivative of t with respect to x here and partial derivative of t with respect to y here are 0. So there is no heat influx in or out. And here the heat coming from the conduction is equal to the heat taken out by the convention, right? So I don't want to get into heat transfer right now, but if you can see here, depending on the initial temperature that you gave to these different points, how you heat it up at time t0. So there is a right-hand side here, okay? But when the time goes on and the solution is stabilized, which means the temperature at any point does not change anymore with respect to time, then we call it steady state. Okay, which means t does not depend on time anymore. We call it steady state temperature distribution in 2D, and you can show that then the distribution of t with respect to x and y follows what you had over there. It should follow this smoothness constraint or Laplacian equation. Again, as long as it is steady state. If it's not a steady state, there is a right-hand side here. So this, you can say, for example, like steady state 2D temperature distribution. Okay, that's one of the applications. Or if it's, let's say, the flow of fluid into this 2D area, and again, depending on what you have on the boundaries, right, one or two sides you might seal, so no fluid can come in or go out, and these two sides you might have different conditions, different pressures, different flow rates, and so on. Then you can also show that for that case of this fluid potential field, if you call the potential field at position x and y, you call it phi x and y, then you can show that in the steady state case where nothing is changing with respect to time anymore, right? Then you can show that as long as the fluid is not compressible and as long as it is not rotary, you can have an equation like this. Again, where, as I said, this phi is the potential field for the flow of the fluid. And the streamlines are perpendicular to the potential lines, as you know. Okay, so that's one of the cases that you have, right? In 2D. Or as I said, you can have a steady state 2D temperature distribution, which comes from this equation. So now that you know these guys exist in heat transfer, in thermodynamics, in fluid flow, in wave, and so on and so forth, higher level engineering courses, now the question is, how do you solve them? So I give you an equation like, let's say, this wave equation. I give you two initial conditions, two boundary conditions, and I ask you, okay, now that I gave you all of that, now you tell me what is u of x and t. So I give you f, I give you g, I give you these boundary conditions. You have the equation, I give you the parameter t and mu, and I ask you for the solution. Can you solve it? Okay, that's the thing. How can you solve that, right? Analytically. That's the topic that we are going to focus in this video. Now, not always these PDEs can be solved analytically. Sometimes you have to resort to numerical solutions, and that's where there are different numerical methods. The one that I'm gonna be discussing in the next video is finite difference method, but there are other methods like finite element, finite volume, and so on. But as I said, in the next video, I'm gonna talk about one of the numerical solving methods, which we call finite difference. Okay, so the first thing is, how do we solve? But before that, I want to mention one important thing about these partial differential equations, and that is there are lots of different solutions that can exist and how you should integrate when you try to solve them analytically. So I need to mention some stuff about that. And then as an example, we're going to go and solve the wave equation. And then we talk about different categories of the second order PDEs that like we categorize them into different categories like elliptic and different things. That there are three main categories, as you know, or maybe you don't know. If you did, you would not be here. But there are three categories of the second order standard formats with constant coefficients, right? And we're going to talk about them, the elliptic form and the other forms too, and which one we can easily solve, the normal form, and so on. So let's get into some discussions. Now, one thing I mentioned is how to integrate and how to solve these equations, okay, when you're trying to do integrations, and the fact that there are so many different solutions for many of these PDEs, and the only thing that will make a unique solution are these boundary and initial conditions. Without this boundary and initial conditions, the solution to many of these many of these PDEs in general, they are quite general with lots of arbitrary functions in them. Now, what do I mean exactly by that? Let me show you. So if I give you an ODE like this, that's the second partial derivative of u with respect to x and y is equal to negative of partial derivative of u with respect to x. So it's second order. Here you have a mixed derivative. Here you have a first derivative. And if I say, what is u as a function of x and y here? Okay, so when you have stuff like this, some of them are quite easy to solve, and all you need to do really here is a change of variable. So if you call this guy here, if you call it like p, then here this right hand side can clearly, you know, you can change the order. Instead of first x then y, you can make it y first. Here is first y then x. You can change it to be first x then y. So you can also write it as partial y partial x, and then this is going to be partial derivative of p with respect to y. Okay, so now your equation is this: partial derivative of p with respect to y is negative p. Okay, so all I did, I changed the variable, right? The first derivative of u with respect to x, I call it p. Now, as I said, my PDE is now converted down into first order from second order, and all I see right now is y, so I can separate the variables, and this is going to be partial derivative of p over p is going to be negative partial of y. Okay, so I did separation of variables, and now I can integrate both sides. If you do that, this you know, partial of p with respect to p, you know, this natural log of p, or if you want to be more accurate, natural log of absolute value of p. And this guy is going to be what? Now here, pay attention to what you get here. So this, well, you might say, okay, partial derivative of y is negative y. That's right. But I tell you what, remember when you do indefinite integrals like this, you always have a constant, right? Remember when we did just regular integrals, when we did indefinite, we always had a constant, correct? Now here you are taking the derivative of a function that the function itself, this p, can be both function of x and y. Okay, this p is both functions of x and y. And so you're doing derivative integration with respect to y. So not only this c can be a constant, actually this c in general can be what? Can be any arbitrary function of x. So it can be something like this. If you don't believe me, take a partial derivative of both sides of this with respect to y, see what you get. If you take a partial derivative of both sides with respect to y, this is going to be what? Partial derivative of p over p. This is going to be negative partial dy, and this is going to be 0, because the derivative of a function fx with respect to y is 0. So when you are doing when you are doing integration of multivariable functions, anytime you are integrating with respect to one variable, the constant could be the function of the other variables. Okay, so here this f of x is arbitrary function. Now from here, if I raise both sides, I do e to the power of both sides, something like this, then here, what would you get? You are going to get p, and here you are going to get e to the negative y times e to the f of x. And this e to the f of x, it is a function of x. If you don't mind, I would call it like g of x. So it is g of x times e to the negative y. And remember here, this p is a function of x and y. And g of x is this guy here. So far, so good? So now, this is the solution to p, but remember, p itself was what? P was the derivative of u with respect to x. So what I do is, I write whatever it was, this was the partial of u with respect to x. So partial of u with respect to x is now g of x e to the negative y. Again, I separate the variables. And if you do, you're going to get partial of u to be g of x times e to the negative y partial of x. And now if you integrate both sides, and here we are doing integration with respect to x on the right hand side. So this is going to be u on the left hand side. This is going to be u of x and y. Here, since neg e and to the negative y does not have anything to do with x, you can bring it out. And it is going to be integral of g of x. And again, you have a constant here. But remember, here integration is done with respect to x. And when you do integration with respect to x, this c can be what? An arbitrary function of y. Because when you take x derivatives from both sides of this, then the derivative of the y equation with respect to x is 0. So instead of this c, I can replace it with what? I can replace it with something like h of y, where h of y is arbitrary. Now, if I call this integral of gx dx, I call it whatever you want to call it, maybe q of x, then my solution, final solution, will be u of x and y is equal to e to the negative y q of x plus h of y. That's my solution. Where q of x is what? Is integral of g of x dx, and g of x is exponential of f of x, correct? And f of x is this arbitrary function that initially you considered, so it is going to be like an arbitrary function itself. So you see here you have two arbitrary functions in the solution, right? Completely arbitrary functions of x and y. They can be anything. So now clearly this is not a unique solution. What makes this solution unique is those initial conditions. So here clearly you have a second order thing, and you need to have partial derivatives at x and y, and the u at x and y set equal to something, okay? So those boundary conditions here will fix and make q of x and h of y unique. Okay, but in general, as I said, the solution to this in general without boundary condition or initial condition is quite general, and you have to make it unique by applying those. Okay, so this is one thing I wanted to say. The other thing I want to talk about is the linearity. Okay, we call an ODE linear just like a PDE, sorry. PDEs and ODEs, the definition of linearity is the same. As long as the unknown function u and its derivatives are of power 1, there is only a linear term in them, from them in the PDE, then your PDE is linear. So if I have something like this, by the way, I would like to use subscripts, if you don't mind, like let's see if I have anything anywhere. I don't. So if I use this notation from this point, I try to avoid those partials and use a brief notation. So if I say uxx, I mean like second partial derivative of u with respect to x. If I say uxy, it means second partial derivative of u with respect to x and y, and so on and so forth. Okay, so I use this brief notation, which is quite common in many textbooks. So now if I give you an ODE like this, is this linear? Sure. Because if you look at u and its derivatives of whatever order, they are all linear terms. There is no power 2 of them, never any of them multiply together. There is no square, there is no sign or anything like that. Now, if I just added a power 2 here, it makes it nonlinear, or added a power 3 here, or multiplied them, right? So that's linear versus nonlinear. The other thing is homogeneous versus non-homogeneous. So if there is any function of only the 2 or 3 or whatever independent variables that you have, so here the independent variables are x and y, but it could have more than x and y, it could have t and more than that. If only the terms in the equation are the function and its derivative, and no independent function of those variables, independent variables, without any, let's say, u in them, like in this case, then we call it homogeneous. Okay, but as I said, if on this right hand side I have a function of x and y but not u, then this is non-homogeneous. Okay, so the definition of homogeneous and non-homogeneous, linear and nonlinear, is very similar to ordinary differential equations. Keep that also in mind, because we need to get to that at some point. The good thing about linear ODEs is this. If I have a linear ODE like this is linear non-homogeneous, but if I find a solution for that, like u1 of x and y, and if there is another solution for that, like u2 of x and y, then I can show you that a linear combination of u1 and u2 is also a solution to this PDE. Okay, so this is that superposition property. So once you have one solution, another solution, any linear combination of them could also be a solution to that. Okay, that's only valid for linear ODEs, PDEs, not nonlinear ones. Okay, so that's another important thing that I wanted to talk about. Now let's go ahead and look at that wave equation. And we try to solve this wave equation, something similar to what we did here, but we're going to apply boundary conditions and initial conditions and get a unique solution for this 1D wave problem in the string, right? So let's solve a problem uniquely and apply those conditions. So you see what I mean by unique solution. So let's say here, as I said, I have the wave equation, okay? Now, what I will do is I will fix the two ends, as I said here. So I will fix the two ends of the string, and I will give it two initial conditions, one for the displacement, one for the initial velocity. By the way, now that I'm looking at this, I made some mistake here, and I'm sorry about it. So it should be f of x, and this should be g of x, not t. Okay, so just please keep that in mind. It's f of x and g of x. Okay, so the method that is common in solving many of these PDEs is what we call separation of variables, and that's what we had also in ODEs, right? That's what I did here to solve my PDE. So the separation of variable and change of variable are quite common. So as I said, what I will be solving is exactly this set here. I have initial displacement, initial velocity. I have two boundary conditions, both ends 0, 0. Now f of x and g of x are fixed functions, okay? They are given functions. They are not just arbitrary functions. They are known functions. Like this could be like a sine of x. This could be like whatever you want, maybe even 0. Correct? How do you solve for that? If you want, I can make them specific. So let's say, for example, here, this is my string. I fix it between two ends, and initially I give it a sine function, something like that, a half sine function, or even a square function, or whatever you want. And I release it from rest. So this is x of 0, which is fixed. This is x of L, which is fixed. The tension in this guy is T, and the mass density per length, or the linear density, is mu. Correct? And as I said, the displacement of any point from its equilibrium position as a function of position and time is u of x and t. Now, if you don't want, I can call this m and l. So that mu and u, because they look quite similar, I rather do it this way. Okay, so my equation clearly is what? That the second partial derivative, as you can see, with respect to time. So my equation is utt is equal to c squared uxx, and c squared, if you remember, it was t over m over l, so it is tl over m times uxx. This is the governing PDE, The boundary conditions are u at location 0 and time t at any time is 0. U at location L and any time is also 0. The two ends are fixed. And I also have initial conditions. And the initial conditions are u at any location x but time 0. The initial displacement is, let's say, a quadratic function. Let's make it simple. And since at 0 and L it is 0, and let's say at point L over 2 it's symmetric, let's say it's some max, so it should be a quadratic equation with a negative thing, so it should be something like negative x times x minus L, correct? So it is like Lx minus x squared. This function is 0 at both x0 and x of L, and the max of it happens at L over 2, where it is L squared over 4, the max. And the initial velocity is 0, so you released the whole thing at time 0 with 0 velocity. Okay, just like, as I said, playing a guitar and moving the string. So you did something like this, and now the question is, what is this u of x and t? Okay, so the method that we are going to use, as I said, one of the methods is using separation of variables. So what you do is this: you assume this solution, whatever it is, you assume this u of x and t that I want to find is a function like f of x and a function of g like of t. So you assume it's the product of two separate functions of position and time. Okay, you can separate it into the product of two univariable functions. Okay, now not always this method works. It mostly works in PDEs where the stuff are multiplied and divided. If you have stuff added together, not always you can use the separation of variables. So now you try to plug it into this equation. Now, clearly the second derivative of, or any derivative of u with respect to time, only involves derivatives of g with respect to time, because f does not have any t derivative. So if I call this equation 1, if I call this equation 2, now I'm going to plug 2 into 1. Okay, so 2 into 1, and you will get f times second partial derivative of g with respect to time. And here I'm not saying f of x, you know it's f of x, and you know this is g of t. By the way, here the partial derivative is converted into a direct single derivative. All right, and the reason is g is only a function of time. So this is going to be like that, and if you don't mind, I would call this again something like c squared, where c is the speed of propagation of wave into this media. And so it is going to be c squared, and second partial derivative with respect to x is going to be g times the second partial derivative of f with respect to x. Okay, because g has no x derivative. So this is what you get, and now if you see, I can separate f and g from both sides. So what I will do is I divide this side by g and that's, or divide this side by fg and that side also by fg. If you do that, then you will get the second derivative of g with respect to time. And if you don't mind, I write it as gtt divided by g is equal to c squared fxx divided by f. Okay, so I separate the two sides into one here, a function that is completely for t, and here something that is completely a function of x, right? Because f is a function of x, and its partial and its derivatives with respect to x should be also a function of x. So this whole thing is pure x function, this whole thing is pure t function. But you know this equality can never be. Never a function of t is equal to a function of x. It's not possible unless both of them are equal to some constant like k. If both of these functions are constant like k, then yes, a function of t can be equal to a function of x. Otherwise, this equality can never be, okay? And that's what you do here. Good. Now, if we do that, then this k is arbitrary, okay? It can be positive, negative number, even 0. If I do that, then you get two equations. One is this one equal to k, which will be something like gtt, and then let's see, minus k times g equals 0, and it is going to be c squared fxx minus kf equals 0, or if you want, we can divide both sides by c squared. So one other thing you can do is bring that c squared here. That's the same thing, it's not going to change anything really. If you want, you can bring that c squared here and get rid of that. So now it is going to be minus k times c squared times g equals 0, and then it is going to be fxx minus k times f is equal to 0. Okay, so you get two separate ordinary differential equations. Now pay attention, each one of these is an ordinary differential equation. So we converted our PDE into two ODEs, and that's the power of this separation of variable if it works. Good. Also, your initial and boundary conditions, you have to apply this separation to them to see what they give you. So another thing you need to do is, if I call these equations, let's say 3 and 4, I want us to apply 2 to 3 and 2 to 4, see what you get. For example, if you apply 2 into 3, what happens? U at 0 and t means what? Means f at location 0, g at arbitrary time t is 0, correct? So let's do that. So let's plug in 2 into 3, see what we get. So far these are our governing equations, but also let's look at the boundary condition and initial condition. So as I said, if you plug that u into the first one, it is going to be f of 0 g of t equals 0. And then f of L times g of t equals 0. Okay, so these are the resulting boundary conditions. Now, here, when f of 0 times g of t is 0, what can be the solution? There are two solutions here. Either f of 0 is 0, or g of t is 0. Similarly, from the bottom one, either g of t is 0 or f of L is 0. Now, g of t cannot be 0, because if the entire function g of t is 0, when you plug it into 2, the whole displacement u will be 0, which is the trivial solution. So this cannot be an interesting solution to me. So the conditions are now what? This function f at location 0 should be 0, and what? F at location L should be 0. And these two now serve as what? As the two conditions you need to solve this second equation. Okay? Similarly, if I try to apply 2 to 4, let's see what happens. If I plug in 2 into 4, then what happens? So if you plug 2 into 4, it means u at x and 0 means f of x, g of 0. It is equal to lx minus x squared. So f of x, correct, times g of 0 is equal to x L minus x squared, and correct, that is a function of x, and the first derivative of that, which comes from the derivative of g at x and 0, is 0, so it is going to be f of x times g derivative of it with respect to time at time 0 is 0. Now from the bottom one, clearly you have two scenarios. Either f of x is 0 or gt at time 0 is 0. Clearly, again, f of x, the whole function cannot be 0, because if you plug it back into 2, the whole solution is going to be 0, and that's a trivial solution. So that's not what we want. So definitely the derivative of the time function g with respect to time at time 0 should be 0. And this is definitely one of the conditions that you need for the first one, correct? Now here, let's look at this one. What does this one give us? Does this one give us anything? So it says whatever g of 0 is equal to this function divided by f of x. Okay? Right? So what can you get from that one? Can you get anything about g of 0 about that? Is there any possibility for g of 0? Well, we're going to take a look into that a little bit later, but what you can get from this one, because you clearly need two conditions for g as well. It's a second order. So we're going to look into this later. But now, since I have the second ODE with the two conditions that it needs, let's try to solve this. So if you don't mind, I would call this first one equation maybe 5, and this one equation number 6. So each equation with its condition, I call them 5 or 6. If I look at 6, what's the solution? What kind of function do I have that's the second derivative of it with respect to its own variable minus a constant times f equals 0? What's the solution here? So first, let's look at a solution to 6. So 6 is like this. F of xx minus k times f equals 0, and then f of 0 equals f of L, and that is equal to 0. Correct? That's what you have. That's the equation for the x function. Now, what's the solution to this first? What kind of function, because this is pure x, right? And this is an ODE, and from what you know from ODEs, the solution to this, depending on the value of k, could be different formats. So here it depends on whether k is positive, negative, and so on, right? Or even 0, because k here is completely what? This k here, when we say they are equal to k, this is and what? This is arbitrary constant, which means it can be bigger than 0, it can be less than 0, it can be equal to 0. So let's look at different scenarios here. So case one, let's look at one of the easiest cases, k equals 0. If k is 0, it means the second partial derivative of f with respect to x is 0. And clearly the solution here is a linear function, like f of x equal ax plus b. Now, if you plug these two conditions in it, at x of 0, f is 0, right? So if you plug now these two into it, you see that b has to be 0, right? So that f of 0 is 0, b has to be 0. And when L is 0, it means A times L should be 0. So if you plug in, you'll see that B is 0, and then A times L is 0. And since L is not 0, then A should be 0. And when both A and B are 0, it means the whole F is 0. And remember, this leads to a trivial solution. So clearly, this is not of interest. So clearly, K cannot be 0. Okay? It's not going to be. So that's not a possibility. Let me call this the dollar equation. So I'm going to plug here the dollar equation. Okay, what else? Well, can K be positive or negative? Let's look at those cases. So case one, let's say K is positive. What does that mean? Well, if it's positive, when you take it to the other side, it is going to be f of xx is equal to what? Since this is like negative of 2 times f, correct? Because this k is like positive 2. When you take it to the other side, it stays positive. And so the second derivative of the function is a positive number times the function. And the only solution for that can be an exponential function. So in this case, your f of x has to be what? An exponential function, right? You know, that's the only solution possible, correct? So it should be something like a times exponential of square root k times x, right? And because this function, if you take second derivative of it, is square root k comes out 2 times, right? And so you would get a times the square root k, and times k, so the second derivative is going to be k times the function itself. And also this function, if you have something like this, correct? When you take second derivative of this negative square root k comes out twice. And when this negative square root k comes out twice multiplied by itself, you're going to get again positive k times that. So the combination of them is the solution. Okay, but now, again, you have to plug in 0 in it, and you have to plug in L in it, and satisfy these boundary conditions. So let's do that. So again, we are going to apply the dollar equations to it. See what happens. If you plug in 0, it is going to be a plus b equals 0. And if you plug in L in it, then it will be a times exponential of square root k times L plus b times exponential of negative square root k times L is 0. And well, here, what's the solution? Well, from the top one, a should be equal to negative b, correct? Or b is negative a. And when you plug it into the bottom one, right, you can factor out a, so it is going to be a times exponential of square root kl plus exponential of negative KL, this thing should be 0. Or negative actually, here, since B is negative A. And this guy here is not 0. These two are not the same, right? So this is not 0, so the only solution is A should be 0. And when A is 0, it means what? It means B is 0. And when A and B are 0, it means what? It means again F is 0. And that's not what you want. So this is also dead end. So K cannot be positive. It cannot also be 0. So the only solution for K, hopefully, is K is negative. We don't know. We have to check whether the negative case can satisfy. So if K is negative, now the second derivative of the function is a negative number times it is. And you know, again, based on your ODE knowledge, that the solution should be a harmonic function. So it should be A times sine of square root K times X plus B times cosine of square root K times X. Okay, and again, here I'm going to apply those boundary conditions in it, the dollar equations. See what will happen. So if I do that, at x of 0, the sine term goes to 0, the b cosine will be 1, so it means b has to be 0. Good, that's your first one. F at 0 is 0. B is 0, so it means this term is gone. So your only solution is a sine of that. Now, the value of that function at L should be 0, so it means a times sine of square root K times L should be 0. And here there are two possibilities. Either a is 0 or that sine of that thing is 0. Clearly a cannot be 0 because if a is 0, b is already 0, f gonna be 0, and that's not what you want. So this is not gonna go anywhere. So now if you can satisfy this equation, that sine of square root K times L, okay, sine of square root K times L is 0, then you might be able to have a solution. Okay? And what does that mean? Well, what values they have sine of them equal to 0? As you know, only integer multiples of pi, 1 pi, 2 pi, 3 pi, 4 pi, could have what? Sine equals 0. So this square root K times L should be like n times pi, where n is what? Like 0 plus minus 1 plus minus 2, etc. And here, this gives you a solution for K. Remember, K was arbitrary negative number, but here, it tells me no, actually there is a solution here for K. Okay, and what is that? It tells me that this square root K that I was looking for should be n pi over L. Okay, and if I replace this guy, let me call it equation, whatever you want to call it. Let's see here. We had 5 and 6. Let me call it 7 if you don't mind. If I plug this 7 back into this solution, right, then f of x will be what? It is going to be a times sine of n pi over L times x. So clearly now you can see that the x portion of the solution is a harmonic function. Okay? And this n in it can change from 0 to -1, +1, 2, and this is generally an integer multiple of pi in the numerator, n pi. Okay, so that's the frequency of that sine function. And this a is an amplitude, okay, that you can find. So far so good, right? So far I found the general format. This a is just a constant. I found the general format of my f portion of the solution. Good. So let me call this 8 because we need it. Now let's go back and look at 5. But before that, if I want to write my general solution, if I want to use this 8 and plug it back into my original format 2, you have to pay attention here that the solution that we found for f, it is valid, but it is valid for what? For all integer values of n. So if I want to write my solution u of x and t, it is going to be any of these f's for any different n values multiplied by the unknown function g of t. And since each one of them provides a solution, each one of these a sine n pi x over L for any value of n that is integer is a solution. When I multiply them by g, each one of them is a solution to the PDE. And since I have all of these solutions and it's a linear ODE, and we learned that once you have some solutions to ODE, the linear combination of them is also a solution. So definitely in this case for a1 and a2 of equal 1, so the solution will be a summation of n from 1 to infinity of a times, okay, or you can call it a n, because for each one of these n's you're going to find a different n, so it is going to be like a n sine of n pi x over L times g of t. So this is the solution. Okay, this is the solution. You say it kind of looks like a Fourier series. It is. So if I call this 9, now instead of going back directly to 5, I would like to look at this new 9 and try to reevaluate this 5. Now 5 is correct, no problem with 5. What we need are these conditions that we need for 5. 5 is still valid regardless of it's 1 or infinite number of terms in the series. 5 is always correct. The thing is this: when we say that f of x times g of t at 0 is 0, what happens? Right? Or if we go back to these conditions, when we say u of t at x and 0 is 0, what does it mean? So here I say u of t with u of x of t, derivative of it with respect to t, correct? But at what time? At time 0, correct? Initial what? Initial velocity. This guy is 0. What does it mean? If I plug this 9 into this, what happens? So the derivative of this guy with respect to time definitely involves the derivative of g with respect to time. Okay, the x function stays. The g, and you take derivative, and then set it equal to 0. What does that mean? Okay, that probably implies that the derivative of g with respect to time at time 0 is 0, right? If you just look at here and plug it right here, that means g of t at time 0 has to be equal to what? 0. And that's the same thing as what we found earlier, right? So this is useful, but before that, what's the solution to g? So this condition is still valid. We still can use this. But what's the solution? Well, from 5, gtt is equal to c squared k times g. Okay, all I did in 5, I took this negative term, or negative k times that, to the right hand side. So that's equation 5. Now, we found that this k has to be what? Negative. So this guy is negative. This c squared definitely is positive, so this whole coefficient is negative. And therefore, since this equation 5 is similar to the equation for f, which is 6, since this whole coefficient is negative, definitely, again, the solution for g has to be a harmonic function. So g of t has to be something like d times sine of the square root of that, which is c square root k times t, plus e times cosine of c square root k times t. So that is the solution, definitely, because we determined k is negative. Now, in this guy, I apply this initial velocity condition. So if this is 10 and this is 11, I'm gonna apply 10 to 11. And if I take time derivative of this, the cosine term will be negative sine, which at 0 goes away. The sine term will be a cosine, which at time 0 becomes 1, right? And when that should be equal to 0, it means d has to be 0. And when d is 0, it means g of t, your time solution function, is going to be e times cosine of c, and for square root k, if you don't mind, I plug what we found for it. Square root k was n pi over l. So here I also use equation 7, so it is going to be n pi over l and then times t. Okay, so this is the solution for g of t. And I call it 12. Good. So now that we found 12, which is the format for g with constant e, if you want, I can go ahead and plug it back into 9. Okay, so let's plug 12 into 9. So u of x and t is going to be a summation of, now this e is a constant term. When you multiply it by an, it is going to be another constant term. So if you don't mind, I just call it anything you want. I might just call it whatever, w of n times sine of n pi x over l cosine of c n pi t over l, where again this w of n is simply a n times e. That's just a coefficient, depends on n. And this n here goes from 1 to infinity. So this is my solution u of x and t. So now let's go ahead and apply that final condition that we had, which was the initial displacement. and that was u at all position x and at time 0 was equal to that quadratic function. Remember, u at location x. Okay, I guess I have something I need to address. My pen is not so happy. Oh, there we go. That's all because of probably not being patient enough. So as I said, I have to say that u at location x and time 0 was xl minus x squared. Now let's, in this function, plug time of 0. The whole cosine becomes 1, so this should be equal to summation of n from 1 to infinity of w of n sine of n pi x over L. And so now the question is, what are these w of n's, so that a summation of these w n's times these sine functions from 1 to infinity will form this function xl minus x squared. And this is exactly the Fourier series, right? What we are going to do is to write the Fourier series for this quadratic function, and we treat it basically as a function which only has the sine term, no cosine term, correct? And find this w of n's. And you know from your Fourier series knowledge, if you forgot, please watch my video on Fourier series, that these wn coefficients will be basically 2 over L integral from 0 to L of whatever this function is, xl minus x squared, times the sine function dx. Okay, definitely they are going to be function of n, and for them I have to basically do the dot product of the initial displacement with the sine functions. If this one matches any of these sine functions, then that coefficient will be maximum. If it is perpendicular to that sine function, that coefficient will be 0. If it's in general here, this is different than all of those sine functions, so none of those w's will be something like 0. And the closer this, as you can see here, the closer this initial displacement is to any of these sine functions, which, by the way, these guys have a name to themselves. In vibrations we call them what? We call them the eigenfunctions, right? Or in vibrations we call them the mode shapes. And this guy here, this frequency of this sine function, we call it lambda n, and this is called the natural frequency of the vibration, natural frequencies. Okay, so based on my initial displacement is closer to which one of these, that mode shape will have a bigger gain in the overall response. Again, I don't want to get into vibrations, but here you can use MATLAB and calculate this. So the parameters we need is n, l, and that's it, right? So here I do a symbolic sims of n and l and x. And I need to calculate the integral of my function, which is x times L minus x squared times sine of n times pi times x divided by L, and the integral of this whole thing from 0 to L, for which you know you need to do integration by part. Now it gives you the answer, and let me write it in a pretty manner so I can understand it better. So this is going to be 4L cubed sine of pi n over 2, the whole thing squared, the sine squared, over n cubed pi cubed, and minus L cubed sine n pi over n squared pi squared. Now note that since n is an integer number, sine of n pi is always 0. Sine of 1 pi, 2 pi, 3 pi, negative 1 pi, 0 pi is 0. So the second term is actually 0, so I'm not going to write it. Sine of pi over 2 times n is not 0 unless n is what? An even number. When n is an odd number, 1, 3, 5, and so on, this is not going to be 0. So if I want to write it, it is going to be 4L cubed sine squared of n pi over 2 divided by n cubed pi cubed. Which again, for even numbers, this is 0. For odd numbers, this is going to be positive 1 or negative 1. But when you square it, it is going to be positive 1. So your coefficient is going to be 4L cubed over n cubed pi cubed. So you can write it as 4 times L over n pi, the whole thing cubed, where n is plus minus 1 plus minus 3. Now here, since we are dealing with positive thing, we can just look at positive 1, positive 3, and so on. Correct? Since n goes from 1 to infinity, so let me just keep the positive cases. So it is going to be 1, 3, 5, and odd numbers. So ultimately, after all of this effort, my solution ux of t is going to be summation n goes from 1 to infinity of 4 times L over n pi cubed sine of n pi x over L cosine of c n pi t over L. Okay? As you see, these gains, these weights of the mode shapes, is proportional to 1 over n cubed. So it means as the mode shape number goes up, the weights of them goes down. In other words, it's only the first few mode shapes will have, those are the ones that have a meaningful gain and a meaningful contribution to the overall solution. The rest of them will have what? A very small contribution. Okay, it's just the first few modes of vibration that are the dominant modes of vibration. You clearly see why, because n goes up, this coefficient, which is the weight of that mode shape, is going to go down so fast. Okay, so that is your solution to the wave. Clearly it's harmonic both with respect to x and t, and it is an infinite series, but again, you can approximate it by only the first few terms of the sine and cosine, as this coefficient very fast goes to 0. Okay, and the reason this is an infinite series is because really a case like this is over a continuous medium, not a discrete system, which has infinite many degrees of freedom, and so the solution would look like that. Okay, again, I don't want to make it a vibration or heat transfer course, but I just want to tell you, when you try to solve a single PDE, which was not really hard, in nature compared to many other PDEs. If you can solve it analytically, the separation of variable is one of the main dominant ways of solution. And when you get to a place like this where different functions of different variables are equal and you set it equal to a constant, you have to look at different scenarios for that constant, positive, negative, zero, see which one will satisfy the boundary and initial conditions, especially boundary conditions, which one do not. And based on that, you move forward, and then you satisfied every single initial condition, boundary condition, and so on and so forth, okay, until you get to something like this. So this will tell you the vibrations of your guitar string. Again, this is the X frequency, this is the time frequency, and this is the weight of the mode shapes, okay? This determines amplitudes of the acoustic wave. So you only probably hear a few harmonics, that's what you say, right? When I play acoustic guitar, I hear some major frequency and it's harmonic. And so what frequencies would you hear? This frequency, and it's multiple of that. So if n is 1, you hear pi over L times x. When n is 3, you hear 3 pi over L. In the t domain, you hear what? Pi times c over L, 3 times pi c over L, 5 times pi c over L, and so on. And you only hear a few of them, not a lot, because as the number of harmonic, this n, this coefficient, goes up to 9, 11, 13, 15, and so on, these coefficients are too small, you cannot hear their frequencies. So you only hear a few major frequencies, which is the original one plus its integer multiples, in this case odd integer multiples, and the amplitude of them is decreasing, okay? So just wanted you to have a little bit understanding and better background about this wave equation. Now, there are other ways to solve equations like this. So separation of variable was one method. Using Fourier transform and Laplace transform are other ways to solve equations like this. And since it takes quite time to describe them, I will leave that for the second part of this video. So if I want to talk about a bunch of things for analytic solution of PDEs all in one video, it makes this video quite long. So I split it into two parts, and I will soon end this video. And in the second part, I will talk about how to solve equations like the wave or heat equation, conduction equation using a Laplace transform or Fourier transform. And I'll talk about those three different cases of second order PDEs that I said, like elliptical, parabolic, and hyperbolic formats of PDEs, and how to transform them into easier ways to solve. So we're going to talk about that also in the second video. I just wanted to talk about one specific things before we finish up this problem. And if you remember this Laplace equation, I said that's the distribution of, let's say, temperature over a 2D area, correct? When it is in steady state scenario and nothing changes with respect to time. So when you have problems like that, which are the solution is only determined by the boundary conditions and the initial conditions are all zero, then I just wanted you to tell you this terminology. Okay, so if the problem is a steady state like that, as I said, and no time variation, we call these types of problems, we call them boundary value problems. Okay, so if you hear BVP, or boundary value problems. That's this type of problem, steady state problem, for which the solution only is determined by the boundary conditions. There is no initial conditions. Now, this boundary value problem, or BVPs, the boundary conditions for them could be of three types. One set of BVP problems are the ones for which the temperature, or whatever the variable is, not necessarily, because temperature is only for one case, where this unknown variable u, let's say here, this unknown variable u is determined and fixed on the boundaries. Okay, so for example, on this boundary you have fixed value of u equal C1. On this boundary you have u equal C2. On this boundary you have u equal C3. And on this boundary you have u equal C4. So if the function itself is determined and fixed on all the boundaries, then we call that boundary problem, we call it first boundary value problem, or sometimes they are calling it Dirichlet problem. So if you hear a Dirichlet boundary value problem, it means the value of the function, whatever it is, let's say in the case of temperature distribution, the temperature is set and fixed at the boundaries. Okay, that's the first BVP type. The second BVP type is when u is not fixed at the boundaries. Instead, the derivative of u with respect to normal to the boundary at that location is set. So if this is arbitrary boundary, and at any point you have this normal line, normal to the boundary. If the derivative of u with respect to that normal is set to some constant, okay, which is basically in a temperature problem, it is like heat flux, correct? If it's potential field, then this is going to be like the fluid flow rate, okay? So it is the change of that variable along that direction. It's the flux of that variable along that direction. So for example here, since the normal in this edge and this edge are along x direction, it is like u of a derivative of u with respect to x are fixed at these two boundaries, and these two, the normal is y, so the derivatives of u with respect to y here are fixed, then we call it what? If that happens, then we call it the second BVP problem. Okay, so I'm just telling you these terminologies because you might hear them here and there, or some people call it the Neumann, which is a German name. If you want to pronounce it in German, you have to say Neumann problem. Okay, so Neumann problem, Dirichlet problem, depending on how you define the values at the boundaries. Sometimes it's a mixed. So at some boundaries, you determine the flux. At some other boundaries, you directly determine what? That variable itself. If a thing like that happens, which is a mix, we call it the third, okay, or mixed BVP, or some people are call it the Robin problem. Okay, many problems we solve, especially for heat transfer, are this Robin type. So I just wanted to tell you some terminologies about boundary value, and you know something about it. But we'll discuss this more in our future problems, hopefully. So I will stop the video right now, and as I said, in the next video we'll talk about solving these PDEs using Laplace transform, using Fourier transform, and talking about those elliptic, parabolic, and hyperbolic types of equations and how to transform them into what we call the normal format, which is easier to solve. And then in a third video, really not a second video, I will talk about numerical solution of these PDEs using the finite difference method. Okay, thank you so much for your attention.